Hi friends, welcome to my lecture 31st on helicopter dynamics, and today we are going to discuss response analysis, which is the solution of the governing differential equation for the rigid blade and the elastic blade. Until now we have developed a repertoire of tools for finding the natural frequencies and mode shapes, and now we will turn to the response part of the equation. I am Dr. Ranjan Ganguly. Now we see that once the free vibration characteristics of the blade have been determined, the next step is to calculate the blade response, which is essentially the solution of the governing differential equation. Now we are going to consider the rigid blade and the elastic blade. The rigid blade, you recall, is in terms of beta psi or beta t, that is the flapping angle, and the elastic blade solution is WRT, which is the displacement as a function of the radial location as well as time. Now let's go back to the equation for flap. So we have our usual inertia term, we have the stiffening term, we have a constant term, and then we have the forcing term. Now this forcing term is of greatest interest to us, that is the m beta bar, because this moment is going to contain motion dependent terms in addition to periodic terms. So you are going to have some terms like beta, beta star, beta double star, and you are also going to have psi. Psi is the time here, and these betas are all motion dependent. Now this is a peculiar characteristics of rotor type system, helicopter system, and to some extent even aircraft systems, is that you get motion dependent forces, and these make your life much more interesting as well as complicated. So one way to solve this type of equation is to assume a Fourier series expansion for beta psi as a solution, and then substitute this expansion on both sides and then try to balance out the terms. So that is known as the harmonic balance method, and we are going to discuss that later. Now, one aspect about the rigid plate solution which makes it simple is that beta is only a function of psi or time. There is no spatial coordinate in this equation such as r. And for the elastic plate, that creates one more level of complexity. So in the elastic blade, we have a partial differential equation. So we not only have time, which is the dot, but we also have space, which is in terms of the dash derivative, and you clearly see here the forcing is a function of r and t, and typically this can be motion dependent and periodic. Okay, now this problem is solved in two parts. First part is we find the natural frequencies and mode shapes of the problem using fz0. Now this we have already done in the series of lectures on Rayleigh rate scalar kin and FEM. Now, once we have obtained natural frequencies and mode shapes, we will use this information to find the complete solution using the normal mode equation. So this is a way to solve this problem, which is somewhat simpler in scope. Now, we actually use a normal mode expansion here. So what we do is that we assume the response due to loading is expressible in terms of an expansion where we take the spatial part as the normal modes or the natural modes, and we create a temporal part which is given by this psi I t, and we take a n term expansion. So this is I is 1 to n. So these are the number of modes being used. So you may use the first few modes like 4 or first 10 modes or something like that. Typically, one of the advantages is that only a few modes are necessary to capture the overall dynamics of the structure. So now go back to our equation here. This is flexural stiffness. This is the inertia component. This is the centrifugal stiffening. And now we are looking at the force. So this is typically motion dependent and periodic. So now let's take a step back, and we already know we cannot solve this differential equation using any simple method. So in general, if you have a differential equation that is expressed as dE equal to 0 in mathematics books and so on, Now, one of the things this equation tells you is that dE equals 0 must be satisfied at every point on the domain, that it should be satisfied at all values of r and t. That's what is meant by the solution of the differential equation. And in the case of many simpler differential equations, we can actually solve them like we saw for the uniform beam, which was non-rotating. We could actually solve that equation in terms of sine, cos, and sine hyperbolic and cos hyperbolic functions. Now, here we are not able to solve this equation, so we use a different type of concept. We take the differential equation and we multiply it by certain functions here, which are the beam functions or the mode shapes. And then we take this and multiply by dr and integrate from 0 to r. So essentially we are saying that this differential equation, when multiplied by this mode shape and integrated across the entire domain, should become 0, and this should happen for all the n mode shapes we are considering. So one of the reasons this operation is performed is to reduce the differential equation to n equations in time using normal mode property. And one of the things this integral is going to do, just like it did for the Galerkin method, is that it is going to remove the spatial part from this equation and only give you an equation in terms of time. Now, this process is very similar to the Galerkin process where the error in the differential equation was minimized. That's exactly what we are doing here. And the property phi r is now being used, or phi j is now being used, rather than the polynomial approximation of the modes y r, which was used in the Galerkin method. So there is a basic use of the Galerkin type of thinking in this particular approximation. Now, if you go back to the Galerkin method, you will see that that differential equation is now reduced to a set of n differential equations. The starting differential equations were PDEs, and now these are ODEs. And these are all more amenable to solution than the previous equation. So we have n equations, and we also know all the frequencies of the system, so we would know these frequencies. And mi is expressed as this integral, si is expressed as this integral here. And of course we have m, we have phi, we have already calculated the mode shapes for the problem, and we also have fz, so we can obtain these matrices and vectors, and therefore we can solve this system. Now there are two possibilities. The simpler possibility is we have no motion dependent forces, then things get easy. The second possibility is motion dependent forces are present, then things get difficult. So let's look at the easy case first. So the first case is no motion dependent forces. So in that case, FZRT is not a function of motion or of W. So in that case, SI is simply a function of time, and so we have these normal mode equations here. Now the PD has been converted to this ODE using normal mode approach. We can now treat the problem as a series of single 1DOF systems, and the first few modes are enough to describe the system behavior. Now there are several methods for solving these problems. There are the Fourier series method, time integration methods, Duhamel's integral method, and so on. Now, all of you who have taken courses on numerical analysis or computation know that there are established ways to solve simple ordinary differential equations, and you can solve those here. You can even use MATLAB to solve these problems. Now, the complicated case comes when you have motion dependent forces, which often happens in helicopter dynamics. So in that case, the right hand side Fz has a term which is just dependent on RT, but it also has terms which are dependent on the motion, that is W, W dot, W dash, W dot dash, and so on. And this essentially happens because of the coupling between a highly flexible elastic blade and the aerodynamic forces. So you do your same normal mode approach, but now the left hand side is all fine, but the right hand side, where you have shifted all the motion dependent terms, becomes more complicated. It has motion present there. So these xi terms are present on the right hand side. And these would have to be brought to the left hand side and so on and solved. That's one way to solve it. So all these integrals come out because of the presence of those motion dependent terms, and so you get a coupled set of differential equations. So that's the coupled set of ODEs. You have this differential equation, looks simple until you start looking at the right hand side, and then you have way too much complexity. So what has happened physically is that this system is no longer a conservative system, and we see that the motion dependent forces cause the system's effective mass and stiffness to change. So the mass and spring have changed, and sometimes these equations result in instability. So these are typically known as aero-elastic instabilities, for example, flutter type of phenomena. And these essentially happen because of the presence of some motion dependent forces. So it is difficult to solve these equations, and the solutions may not converge. You may need to use some numerical method to solve it. And typically Fourier series and time integration are used for the solution. So in the next lecture, I am going to discuss some methods of solution for periodic differential equation, and then we are going to embark on the response solution for the problem, because in many practical situations you want to plot this beta psi versus psi or WRT with respect to R and T. So these solutions are very useful for our physical understanding of the system, and therefore the response solution plays a very important role, probably as important as the solution of frequencies and mode shapes. So I'll stop this lecture now. I'll see you in my next video.